In Studio 314, we're lucky enough to have our very own Moog modular voltage-controlled synthesizer. These types of hardware synthesizers were first developed by Robert Moog in 1964, and even today are valued and highly praised synthesizers. The Moog is a modular device, which means that it is made up of a number of various interconnected components encased in a cabinet. These components are each responsible for either generating or in some way manipulating a signal, and all contain their own inputs and outputs. For instance, the oscillator module, of which our Moog has many, can generate a number of different waveforms. It is also important to note that this is an entirely analog synthesizer, which means that a voltage is generated and passed through the components of the synth. We can control the signal flow, or the path that the voltage is taking, by connecting the various components through patch cords, which in this case are unbalanced quarter-inch cables. Any synthesizer begins with the oscillator, which is responsible for generating the signal or electrical current that we'll be manipulating. This signal is presented as a frequency measured in hertz. The human range of hearing, for example, is between 20 and 20,000 hertz. The most basic wave an oscillator can produce is a sine wave. Other waves are also available, each of which differs in the present harmonics or distortion introduced into the signal. Here, we see that the Moog can produce sine waves, triangle waves, sawtooth waves, and rectangle waves. For more information on these different waveforms, refer to the links provided with this video. You can control the frequency of the oscillator using this pot, short for potentiometer, or knob. The range knob controls the octave by dividing or multiplying the length of the waveform being generated. Now, let's say we want to immediately send this sound out to our speakers. The trunk line, found below the oscillator, is where our signal gets sent out into our patch bay. Take a patch cord and connect the oscillator to trunk line 1. To hear the signal, patch the Moog trunk line on the patch bay accordingly. Taking a step back, let's instead patch our oscillator into the VCA, or voltage-controlled amplifier input. This module is responsible for controlling the amplitude of an incoming signal. If we patch the output of the VCA into the trunk lines, we can send our signal out again, this time with the ability to control the amplitude of the oscillator. This is a basic example now, but let's say we want to place a filter into our signal flow, allowing us to subtract out parts of the signal. To do this, patch the oscillator into the LPF, or low-pass filter. A low-pass filter is used to subtract out the higher frequencies in a signal, and lets the lower frequencies pass through. You have controls for fixed control voltage, which dictates at what frequency the signal begins to be cut off. From here, we can again patch our filter into the amplifier, and the amplifier into the trunk lines. We could have also patched our signal through a high-pass filter, which does the opposite of the LPF and lets higher frequencies pass through while attenuating low ones. Both of these filters are tools in performing what is known as subtractive synthesis, which involves taking more complex waveforms and sculpting away the frequencies you don't want to create a new sound. An example of a more complex waveform could be the Moog's white noise generator. This module generates white noise, which is a collection of all frequencies generated at equal amplitudes. This could be considered a complex waveform since it contains multiple, in this case all, frequencies. Now, Instead of our oscillator generating a simple sine wave, we have our white noise generator patched into the high-pass filter, where we can subtract out any lower frequencies we want. From there, once again, our filter is patched into the amplifier, where we can adjust the amplitude and is sent out through the trunk lines. This is a more complex example of subtractive synthesis. It's worth noting that all of the modules mentioned and the techniques used are still what drives synthesizers, both hardware and software-based, today. Synthesizers found in Logic, for example, are built upon the same concepts of signal generation, flow, and manipulation found on the Moog or any analog synthesizer. Oscillators, for example, aren't just found here on the Moog. They, as well as filters, envelopes, amplifiers, and noise generators, are all present in some form in Max, Logic, Reason, Pro Tools, and most of today's music hardware and software.